we want to study the basic physics of these things. And to do that, yeah, we use SNS Josephson junctions. So in the normal conductor could be replaced by semiconductor nanowires or topological insulators. So in this structure, this is basically behaves as a Josephson junction. But if you think about the quantum state formed in the normal region. So normal region, the electron is refracted as a whole, leaving the Cooper pair here. And this whole is refracted as an electron, leaving again the Cooper pair on this side. Then this forms the so-called Andreev bound state. And supercurrent could flow through the Andreev bound state. And the spectrum of the Andreev bound state is like this dotted line with a periodicity of 2 pi. Then the current, the supercurrent is expressed, but just the ordinary I sine phi, like in the tunnel junction. But in this case, the current phase relationship can be more complicated in this case. But we assume it's behaved as a simple current phase relation with sine phi. But when it is predicted in theory that when the nanowires or the topological, this N region become in topological phase, it should show this kind of energy phase relationship. So now it crosses zero energy, then Majorana may appear at this position at zero energy. So this is my simple image how the Majorana zero mode appears in the device. If you have nanowire, on top of that, you deposit the aluminum superconductor. We may have zero modes like this, and we have 2D topological insulator. Then this is edge channel. So again, the zero mode appear like this. And so we want to study the current phase relationship, the energy phase relationship, how it is different, how it can different from the ordinary Andreev bound state spectrum, like the dotted line. So to do that, we use AC Josephson effect, the William Oliver's talk in the very beginning talk, he mentioned about it, the Josephson junctions. It is governed by these two equations, and usually it is SIS insulator tunnel junction, but in our case, it's a SNS junction. It's not necessarily same, but we assume that it behaves similarly, and we want to measure, somehow we want to measure this, the blue one or dotted one. So if the junction is biased, the voltage bias, you know, the current oscillate with a Josephson frequency Fj. Yeah, if the current phase relationship is like this for the topological case, then the AC current would have the frequency half the Josephson frequency. And that is what we want to measure. So first, the maybe easier experiment is to measure the IV characteristic under the microwave irradiation. In the usual case, the so-called Shapiro step is should be measured, like the staircase type IV characteristic. And it is actually observed many, many years ago. But in this case, if you assume the ordinary current phase relationship, like 2 pi with 2 pi periodicity, you see, we should see all the steps, 1, 2, 3, 4, 5. But if the 4 pi periodicity, there is a 4 pi periodicity in the topological case, maybe the odd step would be missing and shown like the red one. So we want to just test it. And first, I show you the result on the experimental result on the 2 cases. Those are experimentally confirmed as a topological, 2D topological insulator. So this is mercury telluride case, quantum well. Actually, this materials was grown in the Würzburg group in Germany, Lawrence Molenkamp group, and we measured it with postdoc and student came to Riken, and we measured the microwave measurement. Then this is a case for the 2D TI case, the Shapiro step case. So you see, there are many things we still don't understand, but you see this the red one with the 1 gigahertz case. First step is missing, second, third missing, maybe fifth missing. But if the frequency is high, we see all the steps are observed. We don't know why. And this is an emission measurement. We tune the chemical potential in the normal region. Then in this case, it's in the conduction band. The chemical potential is in the bulk conduction band or bulk valence band. So it should be a trivial case. So we see the emission with just the ordinary Josephson frequency. But when the chemical potential was tuned in the topological gap, so the measurement result is more complicated like this. So this is Fj ordinary frequency, and on top of that, we see some emission of the half the Josephson frequency. Maybe this is an indication of topological junction, Josephson junction, but this is, we do not think this is proving the existence of Majoranas. And another example is the tungsten ditelluride, the monolayer one is predicted to be the 2D Ti again. This is a 2D van der Waals 2D material.